Okay, so let's see. We're trying to compute a line integral of some vector field here. First, let's draw up what the curve is. Well, the curve is the boundary of something. So the first thing I'm going to do is forget about the boundary curve. Let's just draw the something. Let's draw the surface. And what the problem says is this surface is the union of a rectangle in the xy plane and a rectangle in the yz plane. So, okay, fine. Let's draw our thing here. So the rectangle in the xy plane is from 0 to 5 on the x-axis and from -2 to 1 on the y-axis. So -2 to 1 on the y-axis. It's from 0 to 5 on the x-axis. Whoa. There we go. So here's my rectangle in the xy plane. And we need a union of that rectangle in the xy plane. Then let's see, and the rectangle in the yz plane, so it's -2 to 1 on the y-axis, and then 0 to 3 on the z-axis. Okay, so there's the union of those two solid rectangles. Is that cool? See the two solid rectangles?
So just in general, so the union, because I was even confused with that, so the union of like two rectangles is just the edge of the rectangle?
No, union means you take the thing and you take the other thing and you consider both of them together as a single thing. We haven't talked about the boundary yet. We're not doing boundaries yet. For the moment, we're just talking about the surface. So, yeah, you're right. We're doing a line integral around a curve that's the boundary of a surface. But for the moment, I want to restrict my attention just to the surface. Let's draw the surface first. And once we know the surface, we'll start talking about the boundary of the surface. So here's our surface. And note that it's an upward oriented in the xy plane. And then it's oriented in the direction of the positive part of the x-axis over here. So note that these are consistent orientations, right? They're both pointing kind of in the same direction as far as this. We've got this solid surface here. Okay, fine. Our curve, though, is the boundary of this surface. So the boundary of this thing is going to be, I have to draw, let me use a different, I'll use the black pen here. The boundary is just this curve here. Right, now we've got to think about orientations, right hand, fingers, curling, etc. And I claim that the orientation is like that. Does that make sense?
Yeah, would it have been safe? I mean, what I also did was I took your information from the problem, or gave me board orientation, then I just did the right hand rule thing. And then I got that the middle that piece along the y-axis canceled, and that's what I knew.
Yeah, it does cancel. That's right. Now, the reason it canceled is because boundaries accumulate.
Yeah, but I just didn't want to. I just didn't know if I could just do what you just did.
Yeah. I mean, this is what I had intended when I wrote the problem, right? Now, what you did is fine because of the fact that boundaries accumulate, but it wasn't exactly what the problem asked you to do, right? Now, that's okay. I mean, it would give you the right answer, and furthermore, you're using this accumulation property. If a grader wanted to be really particular about it, the grader could say, well, what you've said is true, but relies on this boundary cancellation accumulation property that you would have to then cite to ensure that what you have written down as a curve is the same as what the problem's asked you to write down. But this is a minor kind of thing. I wouldn't worry about it.
Oh.
Yeah. But this makes sense?
Yeah.
Okay. Is everybody else good with this surface? And everybody see that this is the boundary curve. Okay. All right, so now we finally have our curve nailed down. Took a fair amount of doing just to figure out what the curve is here. Now we want to compute a line integral. We've got a vector field, and we want to compute the line integral. Okay, so we're going to use Stokes' curl theorem here. Big surprise, this is the section on Stokes' curl theorem. So we're computing a line integral over the boundary curve. Let's see, let's call our surface S, by the way. our surface S. And so over the boundary of S, line integral f dot dx. And we want to compute the flux then through that surface of the curl of f dot ds. Right, so we're going to compute that by instead computing this. So we're going to need to compute the curl of this vector field, and I hope this turns out nicely. Let's compute the curl of f here. Let's see what f is. X squared minus z cubed. Let's see, y cubed minus e to the y. Z squared minus x e to the z. All right, so the curl is, okay, well, that's going to be the y partial of that is nothing. The z partial of that is nothing. Okay, 0. That's nice. Okay, let's see, now the second part is going to be the x partial of that, which is 2x, minus the z partial of this. Oh, excuse me. Sorry, I said that wrong. The z partial of this, which is, let me write this down, minus 3z squared, and then minus the x partial of that, which would be then plus e to the z. And then finally, the last component is the x partial of that, which is clearly 0, minus the y partial of that, which is clearly 0. So I get 0 there. Cool? All right, so good news. Let's look at this process. Let's look at this expression here. We're computing flux of this curl that we just computed. That's this guy here. Dot our unit normal vectors over each little bit of surface. And these unit normal vectors are easy to write down. This over this, what you might call S1, right? That unit normal vector, which you might call N1, is clearly 0, 0, 1. And on S2, that little unit normal vector there, which you might call N2, is clearly 1, 0, 0. And in both cases, note that the curl dot this normal vector, well, the dot product of these two things is 0 because it's mostly zeros, and it's just everything has a 0 in it. So this dot product on that surface is going to give you 0.
Okay, that's
Is that cool?
yeah. Because what I had, so when I got to that step, I had four normal vectors, and I was wondering how would I find like another normal vector, like I guess, like on the plane, because I wasn't sure if I could take the cross product of those two normal vectors.
Nah, I mean the beautiful thing about this, I mean the way the curve was given is it was given as the boundary of a surface, and the surface was just described geometrically, and so you can just look at the picture and say, well, there's my unit normal vector for that bit of surface, and then this bit of surface here, well, it's described as part of the YZ plane. I never labeled my Z-axis there, but this is part of the YZ plane, and so it's it's oriented, toward the positive part of the x-axis. So the orientation there has got to be that. So yeah.
So what if like the middle component wasn't 0 in both? Like
on these?
Yeah, in both.
Well, yeah. Then then this dot product would not end up being 0. It'd have a bunch of this stuff in it, and then you'd have an area. You'd have a scalar surface integral to deal with.
So how would you figure out n then? Like if. Like
well, it depends. I mean, the way you figure out the normal vector depends on how the surface is given. If there's a large number of different ways that you can describe a surface.
So I could just choose one of those normal vectors and then do the dot product, or I don't know, like would have to find like a.
Well, I mean, you can't just choose one. I mean, you have to.
I mean, if the surface oriented like so, okay, if we're oriented like that, as it's like counterclockwise, then I could just choose the normal vector like in the xy plane, and that would be the normal vector do the dot product.
I'm not entirely. So maybe I better write this out in a little bit more detail. Yeah. So let's look at we're trying to compute line integral. Stokes' curl theorem says the line integral can be computed as the flux of the curl, and of course flux can be written as with this dot product with the unit normal vector. So let me take this and sort of keep going now. So this is, well, I'm going to say it's flux through S1 plus flux through S2. So I'm going to break up the whole surface into these two pieces. These two separate pieces, S1 and S2. Is that cool? Yeah. Okay, and now each one of those I can write down. Flux through S1, well, here's our curl vector. It's 0, negative 3z squared plus e to the z, 0, dot. Now, on S1, my unit normal vector on S1 is 0, 0, 1. And then I have to say plus, now flux through S2, flux through S2, curl, dot. Now I've got to write down the unit normal vector on S2, and on S2, on S2, my unit normal vector is that, 1, 0, 0. Now, the lucky, super lucky break is that it happens to work out here that both of these dot products are 0. That dot product is 0, 0, 0, 0, 0, 0, 0. So I happen to get 0 plus 0 equals 0. So that, lucky break, right? But notice you have to break the original flux integral up into two pieces. On each piece, you have to choose the correct normal vector. You can't just use this one for that. This normal, that's not the normal vector for this surface, right? Does that make sense?
Yeah, that makes perfect sense.
And also, lucky break, that S1 here happened to be flat. So the normal vector was constant. Now, that's not always the case. I mean, if this surface happened to be like, if it were a hemisphere or some wacky surface that was the graph of some non-constant, who knows what, right? Then this is going to have formulas in it. You'd have to, it might not be obvious how you'd compute this. You could use the parameterization trick from chapter 5 or a variety of different other things that might work out. But yeah, here it was lucky break, and we happen to get these awesome unit normal vectors.
Thanks.
Is everybody good?